Okay, so yeah, welcome everyone to, I guess, our fourth AI-SDM seminar. And this one is going to be about public health decision making. So that's one of our use cases. We heard about disasters last time from Robin, and Bryan is, I guess, our lead expert on this, on the health decision making side, at least at CMU, and he's going to tell us about his work. So take it away, Bryan.
Yeah, thanks, Arti. So today I'm going to talk about a range of projects in public health decision making. And I mean, in the spirit of more, looking for kind of common ground and things to collaborate on, I'm going to give like a purely like high level overview talk of, several different lines of work instead of, talking about a ton of technical detail in any individual area. But so in the spirit of that kind of high level overview, so my work, broadly focuses so this slide was actually made before the center was, created, but appropriately, my work focuses on machine learning for social decision making, and so topics like how we, allocate, scarce resources in ways that are robust to the problems that we often find in, real data, thinking about issues like, causality and fairness that are necessary to do equitable decision making. And so on the one hand, developing those kinds of methods, and on the other hand, working with practitioners to apply them in high-stakes social settings, in particular applications in public health and medicine. And so on the sort of the technical side, I work kind of across this, spectrum of areas that we need to, go from data to decisions, right? That we need to work closely with domain experts, but then to think about the process of, both, starting from how we gather data, right? When doing so is expensive, or, as it is in many settings, how we use that data to train machine learning models, but then not just stopping at prediction, but figuring out how we use those models to drive decision making via optimization that models decisions under constraints, right? When we have scarce resources. And then finally, there's lots of interesting challenges that come up in this last mile when we have the methods developed and we want to be able to actually deploy them in the real world. And then not just to deploy them, but to be able to actually measure their impact, right? To evaluate them and to tell if machine learning is working in the setting and what we can do to improve it. So I work across the sort of range of technical areas. And right now from the health side, my work focuses mostly in these two domains. First, infectious disease surveillance, right? So how we track the spread of infectious diseases, monitor health disparities, understand things like changes in treatment effectiveness over time. And then second, in maternal and child health, where we want to be able to predict adverse events during pregnancy and early childhood, and then to be able to find targeted preventative interventions that can be delivered at scale. And so this talk is going to focus on this process of going from noisy, biased data that we often see in health settings to trustworthy decisions. And there's two high-level directions that I'm going to talk about here. So the first is how we should train machine learning models that are going to be used as the input to constrained decision-making and optimization. And second, how we evaluate the performance of decisions made by either humans or by algorithmic systems under the kinds of challenges that are very commonly present. And I'll talk about a range of these kind of statistical issues that are very often present in health settings. So starting out with this first line of work, so the setting that I'm focusing on here is what are sometimes called predict and optimize problems. So the idea is that we have an objective function that we'd like to optimize. And so this is a function of both a decision variable x that models maybe how we're going to allocate some scarce resource, and then also a parameter theta, which is unknown to us. And this describes the state of the world and determines the impact that our actions are going to have, right? So the objective function depends on both of those quantities. And so the problem that we'd like to be able to solve is to maximize our utility over the decision variable x, given knowledge of the parameter theta. But in this class of problems, theta is itself unknown, right? And it's something that we have side information about. There's some features or covariates that are informative about theta. And so we're going to build a machine learning model to try to predict what theta is, given that. So one example of a problem in this framework that we worked on in the past was tuberculosis medication adherence problem. So this is a huge challenge in delivering care for tuberculosis is that you need to take this like 6 months long course of antibiotics, and lots of people drop off partway through that process. And so health workers will often have these kinds of dashboards, right, where there's something maybe like a digital adherence technology of some sort that allows them to see some indication of whether patients took their medication on previous days. And then you want to use that to predict, right? You want to predict who's most likely to drop out of treatment in the future, given the historical behavior. and then use that to optimize interventions by community health workers, right? They can call patients or actually, do home visits, right? And try to get patients back on track or, resolve whatever obstacles there are to completing treatment. And so the typical way that we think about building systems for these problems is what I'll call a two-stage approach that separates prediction and optimization. So we start by training a predictive model to maximize some surrogate loss function, like whatever, some metric of accuracy. And then we take its predictions and we plug them into the optimizer. And then the optimizer is some algorithm that knows about all of the constraints on decision making and what our objective function is. And it uses the predictions that are the point estimate of theta to then go through and output a decision. And so the challenge with this framework is the potential for misalignment between how we measure success at the different stages here, right? We trained the predictive model to maximize accuracy, but at the end of the day, we just wanted good decisions, right? We don't care about that intermediate accuracy by itself. And so there's the potential here, it seems, to improve the quality of decisions that we get out of this combined system by aligning how we train the machine learning model with what we actually care about at the end of the process. So if we could take the knowledge about how the predictions impact the optimization algorithm, and then feed that back, right, to propagate a reward signal that was at the end, how good was the decision, and then we can update the model to make it induce better decisions, not just more accurate predictions. So the challenge here is that this, seems to involve an operation that's like differentiating through optimization, right? There's, a loss function at the end here that's about decision quality, but then I need to say how changes to the predictions, right, or the parameters of the machine learning model impact that that result of the process, and that depends on a quantity here that I've written dx star d theta, where x star is the solution to the optimization problem, right? So the decision itself, and you need to measure how that changes with respect to the predictions that you make. And so this is challenging because machine learning and optimization typically speak somewhat different languages, right? Machine learning everything is in continuous domain. We like to train systems with gradient descent. But a lot of the time when we're measuring constrained allocation or scheduling or planning or routing, right, all of this is fundamentally kind of discrete in some sense. If a health worker goes one place, they can't go to a different place. They can't be half in one place and half in the other. And so there's a kind of fundamental challenge here with how you propagate information through fundamentally discrete optimization problems. So there's a couple of approaches that we've kind of developed for this over the last few years. So one category of approach is what I'll call differentiable relaxations. So the idea here is to build some continuous relaxation of the discrete problem that then you can differentiate through as a continuous surrogate during training. And so, for linear programs, this can be relatively simple, that, if you have an LP in standard form, then if you add a strongly convex, penalty of some sort to the objective function, then you can show that the solution becomes differentiable as a function of theta. And you can think of this as kind of like shrinking the solution away from like the corners of the polytope where things are not differentiable. So this is, the kind of basic idea that then you can pursue for other classes of optimization problems, right? So for example, you can extend this to mixed integer programs by using cutting plane solvers to build kind of like, more informative LP relaxations at every step of optimization that then you can apply these same basic ideas to. And then, for other classes of optimization problems, we might look for kind of surrogates that are a little bit farther from the original description. So we might look for, heuristics about, simpler surrogates for optimization that maybe we can differentiate through during training. So this is, one kind of, class of approaches that you can take. And another one sort of that we've been working on more recently here is about sort of directly learning surrogate loss functions themselves instead of surrogate optimization problems. And so the idea here, this is in a recent NERVS paper led by Sankit Shah, is to try to directly approximate the loss landscape that would be induced by optimization. So for example, you can imagine if I'm predicting two parameters here that are shown on the x and y axes, then the quality of the decision that I get is going to be some piecewise constant function in this space, typically for discrete optimization. So if I'm on one side of the line, I'll make one decision and get one utility, and if I'm on the other side of the line, I'll get I'll make a different decision and get a different utility. And so this is, of course, a simple representation, but a lot of the time that these spaces are kind of more high dimensional and, difficult to represent explicitly. But what we could do is just take samples of points in the space, right? I can just generate predictions, solve the optimization problem, and then on the training data, I can ask how much do I like the answer, right? I can evaluate against the ground truth that's known to me in the data set to evaluate my utility for the decision that would have been reached. And then I can just fit a parametric model to that process, right? And in this paper, we describe, at least some, initial steps towards good parametric families that kind of reflect some of the intuition that we have about what characteristics are important for doing well at optimization. But once you fit some, smooth parametric optimization, then you can directly differentiate through that when you're training, right? So you do kind of this, only one step that involves solving the forward pass of the optimization problem, but you never directly backpropagate through it because you have now this much nicer surrogate to work with. And so, so I'm not going to show kind of experimental results from all of these different papers over the years. I'll just show kind of one snapshot back in this original motivating domain with tuberculosis treatment. And this was evaluating a problem where we wanted to predict medication adherence and then schedule health workers to visit different locations in the city where they could intervene with different subsets of patients. And so here we're comparing two different approaches to this problem, both of which use the same underlying architecture for the predictive model, right? So they're both using, in this case, an LSTM to forecast future medication adherence, but they're being trained in two different ways. So the first is, the blue bar here is where we train using standard loss function, in this case, cross entropy, for like the binary classification task of whether a patient's going to take their medication. And then the second is where we put the LP that models that scheduling problem into the loop with these kind of continuous relaxations. And so this illustrates this kind of divergence, right, between the two different ways of quantifying success of this problem. So if we care about, in this case, the average value of the objective function, which is the number of missed doses caught by a health worker in a typical week, then we get an improvement in quality by incorporating this objective about decision-making into the problem. And then by comparison here, if we measure according to a standard measure of predictive accuracy like AUC, then, so it looks like the two-stage model is doing what it's optimized to do, right? It gives you something that is accurate according to this metric, but that might not be what you actually care about at the end of the day. And so I think, broadly, apart from, sort of the details of how you architect these systems, which itself is an interesting technical topic, this just illustrates the importance of aligning incentives, right, for your predictive models, right, that you're actually training them to do whatever you're actually going to use them to do at the end of the process.
So, Bryan, in your second approach that you talked about, what's the role of uncertainty there? Like, I was trying to reconcile it with, right, like the standard way you think about it. Oh, you need to learn the function well in places that are relevant to the decision, but not in places that are not. And so you can do some kind of trade-off in terms of how much uncertainty you can tolerate in different regions. So I was trying to align what you were talking about in the previous slide. With that, could you help?
Yeah, so this is a great question. And so right now, so the samples that we're taking here are not in the original feature space, right? They're in the space of predictions.
Mm-hmm.
And so there is an analogous question that arises here of, what regions of this space of predictions do I have to fit well to do well at optimization? And so in some sense, we've just pushed the problem like up one level. So I think the intuition here is we can do a couple of things. First is that we can sample predictions that are kind of in the neighborhood of like a pilot two-stage model, right? So you can, if you think that machine learning models are more likely to like output predictions in some particular subspace, right, then you can try to learn better in that space where predictions are actually likely to reside. And then the second is that you can try to put some of that intuition in the parametric family that it's, so for example, there's kind of properties like you want to be good at capturing asymmetry between underpredicted and overpredicted, right? Or you want to be able to capture the importance of pairwise correlations between variables, right? And you can try to make sure that those are like easily learnable by the family you select.
Yeah, like, so for example, here, the decision equal to 1 may be more relevant than decision equal to 0, right? Like you just care about where there will be an effect. So it's not as important, like, it's not as important to like learn correctly the boundary necessarily.
Yeah. So what's being really what we're like regressing against here is the, I guess, like what I'm showing have is the color, which is the utility of the decision, right? So you're learning to predict the right, like the utility if you were to run the optimization algorithm and get a decision, not the intermediate decision itself.
Is the utility of the decision in the particular example of the results you showed?
Yeah, so there the utility function is, so in the historical data, we can observe when a patient, stopped adhering basically, right, when they started missing doses. And the objective function is that we schedule a health worker for to intervene with that patient on or before that day in that week, right? So we don't directly have the ability here to measure like the sort of like the counterfactual, like would the patient, have changed their behavior if they got the intervention, but we can at least measure like if we would have put the health worker in kind of like in the right place at the right time to do something.
So it's in time. The metric is time.
Yeah, it's whether there's an intervention within a particular time window. Okay. Any other questions about this line of work? Okay, so then I'll switch gears and move on to the second high-level question here, which is how we evaluate the performance of historical decisions. And there's a range of issues that can come up here, and I'm going to start with one, which is correlations in treatment assignment, and to kind of unpack what I mean by that. So a very typical setting is that especially kind of related to these decision problems is that we want to evaluate an algorithm that does resource allocation. So, given some population of n people, we have a resource that can only be given to k of them because we have a limited budget, health workers only have so much time, whatever else. And then we implement an algorithm for doing that. So then how do we evaluate the results, right? Is this algorithm doing a good job? Is it doing better than some other policy that we could have used to decide who gets that resource? And so this introduces a challenge. So even if we can do randomized trials of these algorithms, it becomes more difficult than normal to design and evaluate and to analyze those trials. So in the typical, RCT, we're trying to estimate this individual level treatment effect. And so I just randomize people to either get treatment or not get treatment, and then compare the difference. But here, I'm really trying to determine the population level effect of implementing one policy or another for doing constrained resource allocation. And so, you could imagine, and people have done this, that you randomize two different policies, right? Like you randomize people in group A to have resource assignments determined by policy A, and people in group B to get resource assignments determined by policy B. And so this means that now within each of these arms, the outcomes are no longer independent, because my treatment assignment depends on whether you got treatment as well, right? Because there's a fixed budget. So maybe if you get treatment, then it means that I don't. And so now suddenly all of the, even if you think that there's no actual spillovers, right, that my disease state does not influence your disease state, there is nevertheless a correlation in the treatment assignment. So we can't analyze the outcomes from all of these individuals as though they're independent. And so, in this sort of like very, very naively, we would be losing a lot of information, right? In the only thing you can say that's truly safe is that I have now, one sample, right? That I executed policy A once and policy B once, even if there's many individuals that are kind of within each of those arms of the trial. And so I think there's a lot of kind of open questions related to, this kind of experimental design and analysis for resource allocation. The specific one that we've worked on so far in a paper led by Ditya Mate is whether we can reduce variance in estimates of the average treatment effect of a policy. And the intuition here is that there's a lot of overlap potentially in what policies do, right? So, policy one, might decide to allocate a resource to the patients in the top row, and policy two to the patients in the on the left-hand side, but then there's, many patients for which they actually recommend the same thing. And so intuitively, this means that, on the one hand, this is not helping us differentiate between these two policies, right, if they kind of recommend the same action. And it's really, where the policies differ that's contributing signal about the difference. And so at high level, it seems like there should be some way to, exploit overlap between policies to do better at evaluating, treatment effects.
So Bryan, here, are you considering settings where you get to decide whether, like to test the two policies, whether you allocate people to policy one or policy, like is it equal allocation, or do you actually like adaptively get to decide?
Right now, I'm assuming like a single shot, like equal allocation. Okay. So the typical way that we would go about exploiting overlap in policies is via, inverse propensity weighting, right? So the idea here is that I can, so especially, right, because in the Bandit literature, algorithms or, policies are typically randomized, right? So they have some probability of giving everyone treatment. So then you can reweight the individuals that were assigned to policy A to match the treatment distribution that policy B would have chosen. And then you can pool all of the samples together and use all of them to estimate the effects of both policies. There's a couple of challenges with this. So one to start off with is that policies are often deterministic in practice. So a lot of the time, people like having kind of like fixed scoring rules that they use to decide who gets resources. And so one way that you can overcome this is to notice that an individual's treatment assignment is still random because it depends on the other individuals in their group, right? So this is exactly what I said earlier, created dependence, between treatment assignments, that my treatment assignment depends on whether you get the resource as well. And so that means that I can basically use all of the samples that I see to approximate the probability that each individual would get a resource just over the randomness in the assignment mechanism in the RCT. And so even if the algorithms themselves don't use any internal randomness, right, we've created randomness by randomizing individuals to the two conditions. And so, if I have access to both policies, right, then I can just draw many, simulations of what that assignment could have been, run the policy, see who gets the resource, and then use that to reweight the outcomes. So, this is, I think, the closest thing that you would do kind of like out of the existing way that we usually build estimators for these problems. It turns out you do run into some additional challenges if you try to do this. So the first is the kind of, I think, like normal challenge, if you're working with inverse propensity methods, right, it turns out to be like really kind of unstable and sensitive to extreme values of the propensity scores, right, that are close to 0 or 1. And we can try to do standard things like clipping the propensity scores or whatever else, and we do those, but it's nevertheless an issue. And the second is that it doesn't generalize particularly well to sequential interventions where we repeatedly interact with the same individuals. And so this is the case in one intervention that we were analyzing data from here. So this is a nonprofit called Arman that will place calls basically to women during pregnancy or new mothers to try to get them to engage with kind of educational content about health. And this happens over a series of rounds, right? There's many weeks, and at every step we can make some number of calls, but we can condition that based on what happened the previous week, right? As we repeatedly interact with the same person. And so the issue here is that it now becomes impossible in the sequential setting to simulate what a given policy would have done under a counterfactual assignment of people to arms, because I can say what the policy would have done on the first step, but then after that, I don't know the counterfactual outcomes, right? What actually would have happened, and then what the policy would have done in response to that. And so the entire kind of apparatus for doing propensity weighting kind of breaks down. So now I'm going to introduce a alternate family of estimators that we propose and analyze here. So the idea is to, given a cohort that's being randomized into two different groups, to notice that, as before, right, there's probably some overlap in the assignment, right? So maybe if policy 1 picks the orange people and policy 2 picks the blue people, then the gray people didn't actually change anything, right? You could have put them in either arm of the trial and it would have been the same. And so we can kind of formalize this by saying that there's a counterfactual trial that we could have run, right? Where this gray person was, swapped between, policies 1 and 2, and everything would have happened the same, right? The algorithm would have picked the same sequence of actions because this person was never given treatment to begin with. And so, although this is a trial that we didn't run, in some sense, we know the answer. We know what would have happened if we did run it. So this is still actually observable. And so, right. And so now, what we could try to do is to just average over these outcomes, right? So we could say that, intuitively in this case, right, like really we should count this person, count half towards both arms of the trial. And, formally, maybe we should just average over these two kind of different assignments, right? Both of which we happen to know the results of. And so we define an estimator where we have these observable counterfactual assignments to be the one where the same actions would have been taken per step, even if one individual was moved between arms. Then our proposed estimator just averages over all such assignments instead of just the realized one. And we showed that this can be efficiently implemented for policies that basically compute scoring rules based on individuals' features to prioritize people for resources. And so, what we show kind of informally here is that this estimator is both unbiased for the average reward of the policy, and it has strictly smaller variance when these counterfactual assignments do actually exist. And so this says that in terms of whatever you're trying to measure, like mean square error in estimating this parameter, you're doing only strictly better by doing this compared to kind of a more naive just sample average estimator. We analyze this empirically. So first on a semi-synthetic evaluation based on real data from a tuberculosis medication adherence platform. So we simulate, we use the model to train, we use the data to train models for patients' responses, and then simulate 2 potential policies. And so this is comparing, so the blue is the naive sample average estimator, and the orange is our proposed one that does this, permutation of individuals across arms of the trial. And we find that we get substantially lower variance in the sample estimates when we apply our proposed estimator, and this results in the average treatment effect as well as the estimates as of every step of the process of interaction.
You are not plotting the human data here. Am I understanding this correctly?
Correct. Yeah. So this is estimates of the average over different simulations, right? Yeah. So this is saying that basically the spread like the variance for the blue estimator is fairly large because depending on the different random realizations of the outcomes and assignment, you get different results.
But you do have the human data for this, meaning can you plot it like you are plotting the model?
So there is human data that was used to fit a probabilistic model of people's responses to interactions, basically. So the human data itself wouldn't be anything like related to these policies directly.
Okay, so these are the predictions after the models are trained on that.
Yeah, this is just using the model to provide kind of like a synthetic simulation environment to assess different estimators.
Okay.
So this is assuming that your policies are given equal resources. Is that correct? Or resource budgets, I should say.
Right. Yes. So I think if they had very different budgets, that space of overlap would probably be relatively small, maybe.
Right.
Yeah.
But you could, is the goal to identify which policy is better?
Yeah, that's typically the
so could you...
It's just we give them both the same amount of resources, then we want to find out which is more effective at using it.
Okay.
I'm not really sure what are the implications of the lower variance. So what does it mean, or why is that important?
So it means that you So you get more accurate estimates of the treatment effect, right? So I mean, it's like error, right, decomposes into bias and variance, right? And we said that both are unbiased, so we have smaller variance. It's directly smaller error in our effect estimates. And then, so this relates to, I think, what is sort of an open question, right, which is to give like valid confidence intervals and p-values and stuff in this setting. But in that setting, right, you should get like smaller, confidence intervals and smaller p-values and stuff like that if you have a lower variance estimator.
Hey, Brian, there's a question on the Zoom chat. I'll just read it aloud. It seems that the models you are creating are very specialized for the use case, and these models are optimized for this specific use case. But how well can these models be leveraged for other related use cases, but where these use cases may not fit into the bounds of the original model?
So if there's like another use case you have in mind, maybe I can say something more specific. I mean, so these methods here basically apply to the setting that I sketched out like on the first slide here, like introducing the setting where we have a population of people, and then there's a limited budget of resources, right, that can be allocated to up to k of those people, right? So the methods applied to these estimators apply basically to any algorithms for problems that are of this form. You could ask about maybe generalizations to like other constraint structures or things like that, and I think it's like an interesting question because it impacts, I think, less the statistical side of things and more like the computational, like whether you can efficiently implement these estimators. Maybe it depends on the constraint structure that you have in mind.
So one of the questions is, can there something more be done in terms of like just policy testing? Because right now you just like shared information across the gray people, right, who both policies do the same on. But it seems like there is more information that can be shared, right? And any thoughts on that?
Yeah, so I think part of the challenge is what you can say in like a very kind of like model-free way, because if you don't want to impose any additional assumptions, right, you don't want to try to like model potential outcomes at all, then you have to be sort of careful, right? Because like you really can't make any assumptions about what would happen if you changed anything about the actions, right, at any step. Like you could probably like it would be interesting to try to like hybridize this maybe with kind of like doubly robust methods where you try to like impose a model on the outcomes that would allow you to sort of share more information and then try to be robust to like violations of the assumptions underlying that model. Any other questions about this so far?
Maybe you are gonna talk about that, but I'm not really sure how are you testing these models against human decisions. So this is not telling me about whether humans are gonna engage in the program or not.
Yes, this is a method for analyzing an RCT where you get data about human engagement, right? So it doesn't substitute for doing that experiment, right, or gathering data about human responses. It just helps with the analysis of that data after, right, to kind of like get as much signal out of it as possible.
But then it's not used for predicting whether humans will engage or not.
No, yeah, like this class of methods just like it does not do that at all.
So this is just saying like which policy is better, but it's not telling you how to get those policies.
Yeah, well, so this last figure is just to say that kind of as I mentioned, so purpose explorations have extremely high variance at extremes, even after trying to control for it. But the bigger picture here is I think that there's kind of a lot of open questions here, right, about how you evaluate resource allocation policies, because it really, changes like a lot of like the standard kind of framework for constructing experiments, right? So, basic questions around how you do valid inference, provide confidence intervals with coverage guarantees, how you design experiments well, right, to have high power, all of those things are, I think, still relatively open in this setting. So then I'll talk about, I think, one more piece of work here, which is now about evaluating the performance of human decision makers in the presence of confounding, right? So it's very natural to ask if we have some existing decisions where people are making kind of discretionary decisions about how to allocate resources. How good are those decisions, right? Are they efficient? Are they equitable? Are they reaching the people who are most in need? And so a very kind of natural way of doing this is to say, like, well, I'm going to predict each person's risk and then compare it to decisions that humans would have made or that humans did make in a data set, right? So if I have a data set that contains a bunch of features of patients alongside their outcomes and a physician's decision, right? I could try to predict patients' mortality risk ex ante and then see whether physicians gave the medication or treatment to people who were high risk. The challenge is that naively, there's the extreme potential for confounding in treatment assignments, right? So doctors probably know something the model didn't, right? Because they actually get to talk to the patient, and the model just gets to see whatever features are in the health record. And so if you observe, some discrepancy between these two, it's not clear whether you should blame the doctor or whether you should blame the model instead, right? And most of us would probably say the model most times. And so the question is when we can kind of get out of this trap, right? Like when can we assess human decisions? And when can we do it without making any assumptions about unconfoundedness in treatment assignments? So unconfoundedness here is the assumption that treatment decisions are fully explained by the observed covariance in the data, right? So whatever features, given whatever features you see, now the potential outcomes with and without treatment are independent of the doctor's decision. And so this assumption is extremely suspect in most applications. So one setting where we might be able to do something is where there's a rollout of a new treatment or intervention, right? So there's some time period, and before that time, no one could have gotten the treatment, right? It wasn't available in that place yet. And then after that, it starts becoming available, and some people get it. And so intuitively, it means that we have some kind of good data before rollout when the no treatment decision is unconfounded because treatment wasn't available in the first place, right? So there's no unobservable that was determining physicians' decisions then. And so we can at least predict this outcome absent treatment that I'll denote Y0, using that data. And meanwhile, once the treatment becomes available, we're not going to make any assumptions, right? So physicians or whoever, health workers, whoever's making this decision could be using kind of like arbitrary, unobserved information. And so what we show is that this setting suffices to partially identify this probability that someone gets treatment conditioned on their potential outcome without treatment. And so the way to interpret this estimate is that it's the treatment probability for individuals who would have a bad outcome without treatment. And in a lot of relevant public health settings, this is really the quantity that we're interested in, right? Because if you look at sort of guidelines for prioritizing people for access to things like COVID vaccines or therapeutics like Paxlovid, right? It's all attempts to identify who's at high risk, which is exactly this, people who would have the bad outcome if they didn't get whatever the resource is. And so in particular, we're going to be able to give bounds for that quantity that depends only on classifiers for the things that we can observe, right? The probability of Y0 in the data before treatment was available, and the probability of treatment assignment given the features afterwards. So in a kind of like two-slide overview of how we go about doing this, so the first step is to note that there's we can sort of easily get an inequality that relates this conditional probability to the two marginals here, the probability of treatment and the probability of the bad outcome. But by itself, this is typically vacuous, right? So if you imagine some real numbers like 30% of patients got Paxlovid and 1% of them died, then this, upper bound is going to be bigger than 1, so it's not very helpful. But the picture can be a lot better if we use the covariates, right? So if we condition on covariates X that are observable, for example, in a patient's health record, so we probably have their age and whether they were diagnosed with a bunch of previous conditions and all of these kinds of things from their medical history, then the same inequality holds now conditional on X. And so now this is going to be much tighter if the numerator or the denominator are close to 0 or 1, which is exactly basically saying that we can fit relatively sharp classifiers for these two observable data quantities using the features X, right? So if the features are relatively good in a predictive sense, then you'll get tight bounds. And now this is something that's only on observable predictable quantities, right? So it doesn't involve any assumptions about unobservables into decision making. So I'm going to skip over, some kind of intermediate, sort of technical steps here to, basically we use like this kind of like family of techniques that's popped up like in the sort of double machine learning and semi-parametric statistics literature to derive kind of bias-corrected estimators for these quantities so that we can get, valid confidence intervals and good things like that, even when the, classifiers for these, the numerator and the denominator might be slow to converge. But so I'm happy to talk about that if someone is particularly interested. But just suffice to say, we do that. And then one example application here is that we analyze human decisions to prescribe Paxlovid, right, which is the main antiviral for COVID, in a large electronic medical record data set. And so the outcome here is mortality due to COVID-19. And so we're exactly asking how often do patients who would otherwise die, how often do they get access to this life-saving therapeutic? And so these are the upper and lower bounds across different race and ethnicity groups that we get out of this framework. And so here, I think the interesting thing is that we get like really sort of non-trivial conclusions without having to make any strong assumptions, right? So for example, we can say that among Black patients, at most, 66% of patients who, again, would die without access to treatment are getting this therapeutic, right? And so that means that we can effectively prove that there's the potential for, really, really large improvements, right? If we can improve the delivery of that intervention, that there's a lot more room to reach patients who definitely, would, like really in clinical terms, they really need to be getting this drug. So, so this is the kind of the punchline, at least, of the empirical results. But any questions about this this kind of framework?
What is your X in this case?
Yeah, so this is so age, previous diagnosis of comorbidities like diabetes, hypertension, COPD, kidney disease, cancer, right? Like all of these things you can extract out of the health record. Those are the big ones. I think we don't usually have labs because it's typically people seen in outpatient settings.
And your source for these data?
Yeah, so this is the NC3 data set. That's so it was compiled by NIH, and it's electronic medical records pulled from 75 participating like health centers across the US. And so it contains about, at least last time I checked, I think it was about 7 million COVID patients, along with some matched negative controls.
Can you go to the previous slide? So if the goal is it to estimate the probability of treatment given that, right, the patient would have had an adverse outcome, right?
Mm-hmm.
So why not, and you're estimating these two separately, why not have a model that predicts the two jointly or something?
Like the numerator denominator here?
Yeah.
Yeah, because that's exactly the thing that like we can't observe, because there's no data set where we both observe like the treatment and an unconfounded observation of Y0, right? Because after treatment assignment, like we're not willing to assume kind of unconfoundedness in that observation.
Okay.
So, but in the before treatment data set, I can estimate this one because there wasn't a treatment, and in the after treatment data set, I can estimate this because it doesn't refer to the outcome.
Bryan, a question from Gretchen. Is the goal to treat patients who would die without treatment or treat patients who would benefit most from treatment? Someone who will die with or without treatment does not need to be treated.
Yeah, that's a great question. So in this framework, without making additional assumptions, we're not able to say anything about the treatment effect, right? Like I can't tell you whether this patient would have benefited from Paxlovid. So that's certainly a limitation that you need additional data or assumptions or both to deal with. The motivation for going after this estimate is that a lot of the time the framework for allocating these resources seems to have been basically this kind of quantity, right? Is that we want to reach the people at high risk, and there's no attempt to like screen people out and say like, oh, we don't think you would benefit from Paxlovid, or we don't think you would benefit from a vaccine. And I mean, there are some things like medical eligibility criteria, right? There's like, oh, if you're taking medication X, right, then you cannot take Paxlovid because of drug interactions. And we do like account for that, right? Like we filter those people out of the data set and stuff like that. But beyond that, there doesn't seem to have an there's not really an attempt to like prioritize based on treatment effect. And that might be because it's like not very well understood, even what the treatment effect is, or, it seems ethically kind of murky to like withhold treatment from someone just because we think it likely won't help, if they're in a kind of a bad state.
Like one question, maybe it's not like exactly related, but like suppose we get like the feature importances of these classifiers, and so we find the subset from X which is most important, and this doesn't strictly align with what a human decision features would be. So what would that mean? Would that mean that the classifier didn't fit well, or would it mean that like our distribution was with I would say small to capture what human decisions usually describe? Like, so what does that even mean?
Yeah, so I think so if you're thinking about it just on a formal level, then there's no need for the classifier to kind of match human intuition, right? So like the validity of this kind of partial identification or giving bounds and confidence intervals and all of that really only just depends on the out of sample accuracy of the classifier or something, and so as long as you're doing well in conventional machine learning terms, that's kind of all you need to kind of like safely apply this framework. I mean, I think as usual, if you see something just like really strange, maybe it's an indication that you haven't like understood the data well, or there's some other problem the way you're using the data set. But yeah, like assuming that you like haven't cross-contaminated like the train and test data sets or something like that. That's really kind of all you need. So importantly, this is not like it's not attempting to like mimic human decision makers process. It's trying to get to a place where we can assess the results of that process without having to understand the inputs, in settings where they might not be observable. So I think we have 8 minutes left. I could, theoretically keep talking about more things, but I think that's probably, both not a good idea to just rush through more things, and it'd be more interesting just to have more time for questions and discussion anyway. So I'll wrap it up here, and thanks very much everyone for being here.
Thanks.
So I have a question about the two policy thing. I guess, okay, that's a setting where you're doing an RCT, you're still assigning patients to one of the policies, but one of them is guaranteed to be suboptimal, right? Like, I mean, probably worse than the other one, right? So shouldn't, like, in what scenario would that realistically happen? Like, would you not still want to optimize, like identify which policy is best while making sure that you are actually also achieving some kind of a best benefit for the patients in that RCT?
Yeah, so you're asking why you don't do like an online kind of
Yeah.
I mean, I think it's an entirely reasonable question. So a lot of the time this happens because you want to demonstrate to decision makers that like the thing you have proposed is better than the thing that they are doing now, right? And so you run kind of like a trial that directly compares those two things, and then you say this one is better, so that you have evidence to convince people to adopt it. So I think, I mean, like in sort of practical terms, that's why this happens.
And is that how people currently do? Like if they're trying out different doses of whatever, or something, or maybe even different drugs, would they just like, would they actually conduct an RCT to decide which is better and just randomly, like, equally allocate? I guess that's what they do.
Yeah, that's
right?
the standard.
Without-
is to just do like a head-to-head.
Without caring for whether the people in that RCT get the best benefit or not, right?
Yeah, and so this, I mean, so of course, like there exist adaptive clinical trial designs that apply online learning algorithms, but they're not like in the majority of cases, that's not what people are use, and yeah, I think there's a variety of reasons for that, from like, basically, either just because it makes everything much more complicated, or because it's kind of harder to, explain the results of analysis to decision makers or whatever else.
So assuming like 10 years from now, this is like we have like a very capable system that does this sort of thing. Where do you see it having the most impact in like real world applications? Like, is there a specific domain or like a use case where you think where you're particularly excited about it?
Yeah, so so a lot of the applications that I'm thinking about right now deal somehow with preventative health, because these sort of resource constraints, I think, are more common in that setting, right, where you really want to think about like scalably, delivering some intervention, some care, like across the entire population. It's maybe less the case, like at sort of like a individual clinical level that like if you have some specific disease that like we're like maybe not going to like give you treatment, that is kind of like less common. So at least that's the class of applications that I'm kind of working on right now.
So there are two types of decision makers here. One is a patient, him or herself, who is going to decide whether to take this medication or not, and the one that allocates the intervention, whatever that is, right? So imagine that you have a better predictor of whether the patient is going to take the medication or not. How could you integrate something like that within your framework?
Yeah, so that's going to be so regardless of the overall framework that you use to kind of like design and experiment to compare policies, then that'll enter in the design of the allocation policy itself, right? That you'll have a predictive model that probably as part of deciding who you should allocate some intervention to, right? Predicting whether someone will need that intervention or if they'll be responsive to it, right? Like all of those things will go into the design of that algorithm itself.
Because right now, each of the patients are only represented by that X. Is that correct?
Yeah,
I mean,
yeah. So this is not like model, so like, yeah, so like the work that I showed is not attempting to model patient decision making at all, right?
Right,
Yeah.
right. So yeah, that's so precisely my question is about this integration and whether or how, especially in sequential decision making, whether you would expect that having such a model would improve the overall predictions of your or accuracy of your framework.
Yeah, so I think that we should use that in the design of the underlying policy for allocation, right? That should absolutely like try to understand patient decision making. But the statistical analysis of the RCT that evaluates the policy should be as close to model free as it can be, right? It should not depend on any particular assumptions being correct about what patients actually do.
So I had another question I was going to ask, but I think what Gretchen wrote is actually getting to the same thing. So maybe you can answer her and then I'll see if my question is not answered.
Yeah, so Gretchen's question is, when comparing two policies, the people for whom both policies make the same allocation, those people don't help at all in distinguishing the two policies, right? So why not exclude those people from the RCT entirely?
So if the question is whether to exclude them prospectively or retrospectively in the analysis, I mean, because I think, prospectively is probably not what we want to do because it like changes the entire distribution of the population and the actions and the response of the algorithm and everything, right? So it's like, it's not actually, because when you actually deploy the algorithm, you're going to include those people, right? So you can't really assess the impact of what would happen if you exclude them prospectively from even being in the RCT. Retrospectively, I think this is kind of like the intuition of what this framework is trying to do, right? It's trying to, instead of attributing them to, one arm or the other, right? It's, saying really they're just part of some like background average effect that's shared by both arms.
So the question I had related to this was like, you could keep increasing the number of people on which the two policies give the same decision. And that's not gonna like, somehow you can't get better and better variance just by doing that. Right? So it seems like the variance reduction effect you're getting is, I don't know where that's coming from.
Well, so because it's variance reduction compared to the like sample average estimator, right? So if you add people, like they get added to that estimator as well, right? So they contribute more variance there, and like you subtract them off in our estimator,
Okay.
Yeah.
It's just that what you're improving on is itself.
Right. Yeah. That's like also the baseline that you're comparing to,
Got it.
Yeah.
What is the next most immediate top question that you want to tackle?
So one question is, exactly about the kind of like online design of policies for intervention. And so, how we, use this combination of things, right? Like, historical data with all of its problems, responses from patients, models of patient behavior, how we use all of that to discover, good policies for allocating scarce interventional resources over, as quickly as possible, right? Using as, few, real data, deployments and all of that as possible. So I think that's the thing I'm sort of most excited about right now. And then kind of, as a corollary to that, then, right, sorting out some of these experimental design questions, right, for, how you actually do that in sort of like a statistically valid way.
Okay. And you don't think that using your toy example could be helpful? So I keep thinking about, developing a toy example to get the data from the individuals that take the intervention of them, in a way that it would be possible to test your algorithms together with perhaps our algorithms or other algorithms of modeling the individual decision maker. This is very difficult to do in the real world, in real examples.
Yeah.
So I keep thinking whether your toy example is something that we can think about implementing in some sort of experimental tool that we can collect the data and use for evaluation of the various hypotheses.
Yeah, no, I mean, synthetic evaluation is important and difficult here. I mean, so I think part of the question is whether we're aiming to assess the performance of the model of human behavior or of the overall decision, right?
From my mind is assessing the performance of what is the benefit of bringing a model of human behavior, a realistic model of human behavior in the performance of the overall system.
I see. I'll have to think about this a little bit, because a lot of the time the issue is that the piece that's not well identified in the historical data is exactly kind of like the human decision piece, like what people would actually do if you gave them a different intervention or something like that. That's the part that you're not really sure about. And so you can try to get at least preliminary assessment of the performance of the kind of like the decisions, right, about like resource allocation by examining like sort of like, simulating different models for human behavior and looking like, do you do well if your model is misspecified, for example, right? Like how sensitive is it to, potential problems in that model? And that's at least, gives you confidence about like going further, right, to like, actually deploying something that you've done at least as much as you can kind of on the historical data. But that doesn't tell you whether the human decision model is itself correct, right? Because you're more treating it as like something in a sensitivity analysis to see like, do you well, even if that model is misspecified.
Yeah, that's so, you can have different models of human decision making, but I think especially in dynamic situations, right? If your policy is static, that was one of the main issues. How do you account for the changes in the decision maker himself? So you need a dynamic model of the patient. And my point is that is going to improve the overall dynamic prediction of your policy.
Yeah, so I think what we can say, like, without gathering new data, like, we can say, if the model is correct, then taking the model into account, will lead us to make better decisions, basically. Or maybe if the model is like at most like slightly misspecified, that taking the model into account will improve matters, that sort of conclusion.
So I think another thing is like, if there were some kind of constraints, shape constraints or something on the reward function itself.
Yeah.
That are informed by human decision making, right? That the algorithms could leverage. Right now, they're not. They're just purely learning the model from data itself. Right. But we might know, for example, if you make like repeated recommendations to people, how do they respond? Right. Maybe they lose interest, or maybe initially they gain interest and then they lose interest. Right. So these kind of insights could be brought and exploited by the algorithm, which currently it's not. It's just going by data.
Yeah, I think this is a really good way to introduce this kind of thing. So it's not like you need like the exact value of some parameter to be correct, right? But you need to have a correct like qualitative description of the dynamics,
Yeah. Yeah. Well, let's hand Bryan again. Yeah, on that note, Gauri, I don't know if you have any models for